fostering a culture of academic excellence and inspiration. The inaugural Ramanujan Memorial Oration was delivered by Shanti Swarup Bhatnagar Awardee Dr. Amlendu Krishnan, Professor at Tata Institute of Fundamental Research in 2018. Followed by Shanti Swarup Bhatnagar Awardee Dr. Mahan Maharaj, Professor, School of Mathematics, TFIR, Padma Shri Professor Maninder Agrawal, Dr. N. Ramarao Chair, Professor at Indian Institute of Technology, Kanpur, Shanti Swarup Bhatnagar Awardee Dr. Naveen Garg, Janki K. Iyer Chair, Professor, Department of Computer Science and Engineering, Indian Institute of New Delhi, Padma Shri Dr. Dinesh Singh, Vice Chancellor, Jammu and Kashmir Higher Education Council, Dr. Anish Ghosh, Professor of Mathematics at the TFIR, and Dr. Apurva Khare, Professor of Mathematics from Indian Institute of Science. The Ramanujan Memorial Oration delivered thus far have been widely appreciated and warmly received across diverse academic and social segments. This year marks the 8th SRINIVASA Ramanujan Memorial Oration, and we are honored to welcome our distinguished guest, Shanti Swarup Bhatnagar Awardee Dr. Nitin Saxena from the Indian Institute of Technology, Kanpur. We express our sincere gratitude to Dr. Nitin for accepting our invitation and for sparing his valuable time to enrich this occasion. Once again, I welcome to all of you to 8th Srinivasan Ramanujan Memorial Oration. Thank you.
Thank you, sir. Now, I humbly invite our Honorable Vice Chancellor, Dr. Yogesh C. Goswami, for the welcome address. Please, sir.
Respected Chief Guest and distinguished speaker, Professor Dr. Nitin Saxena ji, Chair Professor, Computer Science and Engineering, IIT Kanpur, coordinator of this program, esteemed faculty members, researchers, students, and participants who have joined this online. Good morning to one and all. It gives me immense pleasure and pride to warmly welcome you in the 8th Srinivasa Ramanujan Memorial Oration, which is organized by Department of Mathematics, Sri Vaishnav Vishwavidyalaya Vidyapith, under the aegis of our university. Today is not just another academic gathering, it's a celebration of ideas, curiosity, and intellectual courage, which was started by a legendary mathematician, Srinivasa Ramanujan, whose life reminds us that true brilliance transcends boundaries of resources, geography, and formal training. Remembering Ramanujan is not merely about honoring the past. It is about inspiring future generations. All of us are inspired by Ramanujan always, who think boldly, question deeply, and pursue knowledge fearlessly. On this meaningful occasion, we are deeply honored to have Dr. Nitin Saxena ji with us, Bhatnagar Awardee, one of the India's most respected scholar in theoretical computer science and mathematics. Really, it's a matter of honor for our Vishwavidyalaya. Welcome, Nitin ji. Yeah. Whose contribution have significantly shaped modern research in algebra, complex theory, and computational mathematics. Sir, your presence add academic value and inspiration to this memorial oration. The topic of today is how to factor algebra. It's both profound and timely. Factoring whether of numbers, polynomials, algebraic structures, or computational objects is at the heart of mathematics and computer science. It represents our deeper quest of understanding complexity by breaking it. into elegant, meaningful components. It's a very interesting, not only for mathematicians, but for all. At this Sri Vaishnav Vidyapit Vishwavidyalaya, we believe that interdisciplinary thinking, where mathematics meets computer science, engineering, and real-world application, is the foundation of future innovation. Events like this oration reinforce our commitment to research-driven education, critical inquiry, and global academic engagements. I encourage our students and young researchers to listen carefully today's talk. This is not only to grasp the technical insights, but to absorb the spirit of inquiry, perseverance, and originality that our speaker shall represent here. Let us interact, ignite new questions, new research ideas, and new academic aspirations. Once again, on behalf of entire Sri Vaishnav Vidyapit fraternity, I extend a warm welcome to Dr. Nitinji, and I thank the organizers for making this event meaningful. With this word, I formally welcome all of you for this oration. Thank you.
Thank you, sir. Now, I request Dr. Satish Shukla, Head of Department Mathematics and Coordinator for today's program, to kindly read the citation of our distinguished speaker, Dr. Nitin Saxena. Please, sir.
Thank you, Nikita. It is a great privilege for me to read the citation for Dr. Saxena. I quote, Dr. Nitin Saxena was born in 1981 and brought up in Prayagraj, India. He did his BTech CSE at IIT Kanpur. He worked on computational complexity, algebra, and number theory for his PhD in IIT Kanpur under Dr. Mahendra Agrawal. Dr. Saxena joined CWI Amsterdam, Netherlands as a scientific researcher. Later, he moved to the Hausdorff Center for Mathematics at the University of Bonn, Germany, with a faculty position from 2008 to 2013. In 2013, he joined CSE IIT Kanpur as an associate professor, where he was promoted to professor in 2018 and N. Ramarao Chair in 2019. He was an adjunct faculty at Chennai Mathematics Institute from 2018 to 2024. He is a founding coordinator of the Center for Developing Intelligent Systems, a new entity to solve governance problem at scale. He is a founding dean of the Wadhwani School of AI and Intelligent Systems, helping center a new organization for teaching, research, and translation. Many famous open problems in the area of algebraic complexity have been solved by Dr. Saxena in his co-authored papers in the last 2 decades. Inventing highly technical algorithmic algebraic tools. He leads globally in a wide area with contributions in primality testing, black box PIT, border complexity analysis, algebraic dependence, factor, root finding, computing topological invariance, and the Has-Welle-Zeta function. Dr. Saxena is a proactive member of the scientific academic community and contributes to the Institute, national, international, and committees and policy making. He chaired the UGCRC to design a modern curriculum for the decades of 2020 to 2030. He is a member of the editorial board of several journals. He chaired the premier CS conference in India. He was served in several program committees. He has mentored 17 PhDs and 26 masters and has taught more than 22 courses, 8 of which are now MOOCs on SWAM. He has given more than 80 invited talks in international and national venues. The key awards Dr. Saxena received are IITK Distinguished Alumnus Award in 2003, MIT Global Indus Technometers Award in 2003, IBM Outstanding PhD Award in 2005, Waddell Prize in 2006, Fulkerson Prize in 2006, INSA Young Scientist Medal DST, Swarna Jayanti Fellow in 2015, Shanti Swarup Bhatnagar Prize in 2018, N. Ramarao Chair in 2019, IIT Bombay International Award in 2023, J.C. Bose Fellowship in 2023, Fellow of all Indian Academies in 2021, 22, and 23. In 2022, DST and Ministry of Science and Technology profiled him of the top scientist shaping today's India. Shri Vaishnav Vidyapith Vishavidyalaya Indore is privileged to present this citation to Dr. Nitin Saxena during the 8th SRINIVASA Ramanujan Memorial Oration as distinguished speaker on 22nd December 2005. Unquote. Thank you.
Thank you, sir. Now, I request our Honorable Vice Chancellor to present the citation to Dr. Nitin Saxena. Thank you, sir. Now, I am honored to invite our eminent speaker, Dr. Nitin Saxena, Professor IIT Kanpur, to deliver the oration. Please, sir.
So can I now share my screen?
Yes, sir. Please.
Okay. Am I audible and is the screen visible?
Yes, sir.
Okay. So first of all, I'd like to thank the organizers, the leading administrators of SVVV Indore. It is very nice that you organize this event every year. And I can see that there are more than, there are around 80 participants. So I think this is a big crowd. I have not visited your university in Indore, but hopefully I'll visit it in the future if I get an opportunity.
Yes, sir, definitely.
So thank you for all the honor. Um, so as already introduced, I will talk about factoring algebraic objects and generally objects in mathematics, which is also now part of computer science. Many of these things, all I do is actually algorithmic. So the topics I will cover or the problems that I will mention, they will be computational problems. If there is any question from the audience, you can interrupt and ask. We can take questions in the middle of the talk also. There is no problem. Okay, so yeah, so we will talk about factorization. So what is factorization? We'll start with very simple examples, which I called base cases. And from these base cases, then we will slowly generalize to more important problems in computer science and in fact in all of mathematics. Now since this is a Ramanujan oration, I should mention that the first problem of factorization is that of integers. And integers, properties of integers is what Ramanujan was fascinated with. So he proved several properties to do with integers, and for that he actually invented, unknowingly or knowingly, some very beautiful new mathematical structures which are being studied, and some questions are open even till today, after more than 125 years. So, or 110, 120 years. So that is what this we'll start with. We'll start with the factorization problem of integers. So even before Ramanujan, this problem was highlighted by Carl Friedrich Gauss in 1800s. That he said in Latin that the problem of distinguishing prime numbers from composite numbers and of factorization is one of the most important and useful problems, and all efforts should be made to solve these problems. So what is the problem of what is our first problem? The first problem is given a number n, let's say 1092, you want to factorize it into prime numbers. So in this case, the prime numbers are 2, 3, 7, and 13. And you can see that actually 4 divides this. So it's the multiplicity of 2 is it's a square. So 2 square divides but 2 cube does not divide. So it's 4, 3, 7, and 13. So you want to find these prime powers. So this is the computational problem. Given a number n, and it will be given in some computer representation. So which is usually it is given in decimal representation. So you are given digits. Each digit is 0 to 9, and so if you are given L digits, you can see that L is around logarithm of n. That is the input size, and that number can you find a prime factor. So input n is in binary, and what you want is something very fast, but what is known currently, this is a big open problem. We don't even know whether we can do this in 2 raised to log n to the 1/3. Okay, so 2 raised to log n to the 0.3. So if log n is 100, which means you have 100 digits, then this is pretty large. This is 2 raised to 100 raised to some number. So 2 raised to 100 is uh, is a long amount of time. You cannot actually solve this in practice. It will take decades and thousands and 100,000 years or even more to actually for the program to stop, especially as n increases. So this is not a practical solution at all, although it is finite time, but it is not practical. So is there a practical algorithm for integer factoring? So this algorithm which I mentioned, which is slightly more than 2 raised to log n to the 0.3, this is called the number field sieve. This algorithm was invented in the 1980s and 90s, and then this area kind of got stuck because this algorithm nobody was able to improve. And the idea for this algorithm is it tries to find two squares which are equal mod n, and then using these two squares, um, assuming that x and y are different, x minus y is used to factorize n. So it's a simple idea, but the implementation is very expensive and nobody knows how to make this faster. So ideally what you want is not 2 raised to log n, 2 raised to something, but just log n raised to something like log n square or log n cube or even log n raised to 10. Is there an algorithm that can run in that much time, which is called polynomial time? And what I have written here is exponential time. So this problem is then considered hard because there is no fast algorithm, even though people have worked on it for 50 years or more. So we believe it to be hard, and its hardness is in fact useful in designing crypto systems. Okay, so already in the first slide of this talk, cryptography appears, and with this is because of a very basic reason. So this RSA is the first most popular encryption algorithm which is used. This is public key crypto system. This is used everywhere. It is used in your communication with through websites like HTTPS. S actually stands for secure, which means it is using RSA. It is used in SSH for file transfer, secure shell, secure FTP. It is used, hence it is used in banks, in all your apps, like example, even WhatsApp. So the security is because of RSA, which is because of the hardness, presumed hardness of integer factoring. So factorization is at the core of not just mathematics, but also now security and hence computer science. So what is the current, what is the most basic algorithm for integer factoring? So that is called Eratosthenes sieve. It's a, it's a very old algorithm from one of the Greek philosophers. And what it does is that it just lists the numbers from 1, 2, 3 to infinity, and you keep crossing out the multiples. So you cross out the multiples of 2, Then you cross out the multiples of 3, then you cross out the multiples of 5, and so on. So as you are crossing out multiples, what remains are the primes. Okay, so this is a test for primality, and it is a integer factoring algorithm. You can use this for also uh, when you try to test whether n is prime, you will find out that it's composite and you will actually find a factor. But you can show as a homework exercise that the time complexity of Eratosthenes sieve is around square root n. Okay, so if your n is very large, then square root n is also very large and it's totally impractical. So at this point, are there any questions? That is the setting. Okay, we'll take a problem, we'll take a mathematical object and then we'll try to factor it. So if you have any questions, you can ask. I am not checking the chat, so I don't know whether there are questions on the chat. If maybe one of the hosts can check the chat, and if there are questions, they can tell me.
So right now there is no questions, and maybe they will
Okay.
ask me last.
Yeah. Okay. So then next object that we pick is univariate, which means now we talk about functions over integers. So univariate polynomials over integers. So this is a very common, very useful object in mathematics, all of math and all of computer science. So here the problem formulation is you are given a polynomial f of x with integral coefficients, for example, x to the 5 minus x to the 4 minus 4x squared plus x minus 2, and you want to factor it. Okay, so now by looking at this, you don't immediately see whether there is a factor, and you don't see the problem is that you don't see the roots. You don't understand what the roots are because roots don't have a direct a closed formula. If it was a quadratic, let's say x square plus ax square plus bx plus c, then you know this formula to find roots of a quadratic, which you learn in high school. It is also called the Sridharachar's formula. Ancient Indians already invented that formula. But what they were not able to find are formulas for cubics, degree 4, degree 5. And this was proved much later in the 1800s that it's impossible to find those formulas. So this is a quintic, this is degree 5. So in general, there is no formula. That was the starting point of Galois theory. So how do we then do in practice on a computer? How do we find roots? How do we find factors? And even how do we test irreducibility? That there is no factor, no integral factor. Okay, so this was done by two brothers and Hungarian mathematician. So this is called the LLL algorithm, L cube algorithm, Lenstra, and Lovash in the 1980s. So what Lenstra, Hendrik Arren and Laszlo Lovac, what they did is they transformed this into a lattice problem, a geometric problem, and they find the algorithm for that for the linear algebra in that geometry. Okay, so they basically do real linear algebra over reals in high dimension. So there they give a nice new algorithm which applies and then solves both irreducibility testing and factorization of integral polynomials in one variable. So this x is one variable. Okay, this is you can actually, if you want, it's a function in one variable, so you can plug in values to x, and so for example, I think in this polynomial f, if you substitute 2, then you will get 0. I think x minus 2 should divide this, or maybe not. Yeah, so you should check whether it has roots. So You can substitute x equal to 2 and see what the answer is. So x is one variable. So you can substitute any number into this. So for this L cube, what they did is they actually, instead of working over integers, they work over a different arithmetic. Okay, the mod arithmetic. So this mod arithmetic is something which Gauss invented, and then Ramanujan and his contemporaries would use a lot, because this is how actually you study numbers, the properties of numbers. So this mod arithmetic, what it does is that it converts a big number into a small number. So what is mod 2? Mod 2 is you divide a big number by 2 and see the remainder. So the remainder can only be 0 or 1, right? So this way you can convert a big number into 0 or 1. So this is what mod 2 does. Mod 4 will convert a big number into 0, 1, 2. Then mod 16 will convert it into a small number like 0, 1, 2, 3, dot, dot, 15, and so on. Okay, so L cube first try to factorize this polynomial modulo these numbers, small numbers, and get factors, and then from those factors they try to learn about the original polynomial. Okay, they try to reconstruct information about the input, which is called lift. So you factorize mod 2 raised to k, and then from there you lift to an integral factor using lattice theory. And this lattice theory which they created, the computational lattice theory which they created, is actually useful in new kinds of crypto systems, which are called post-quantum crypto systems, which are secure against quantum algorithms. Okay, so if there are quantum computers in the future, then you cannot use RSA. You have to use something new. So that is provided by the lattice design. So that is the beauty. In the first slide, you see one crypto system, and in the second slide, you see even a stronger crypto system. So as you study more objects and try to factor them, you will actually understand the foundations better, and it will not only lead to understanding, but it will also lead to new kinds of algorithms and systems. So with that spirit, we move to the third object, which is univariate function or polynomial over finite fields, not integers. Okay, so this is the picture of Galva. So Galva died very young. He died in when he was aged early 20s. And already he had developed this theory, which is now called Galva theory, which is what is shown in this picture is polynomials. From polynomials, he looked at field extensions, and from field extensions, he looked at groups. Okay, so this q square root 2 square root 3 is a field extension, while this f and g are actually group elements, which is called the Galva automorphism. So these are actually permutations. So from roots, he moved to permutations. And then he gave very powerful connections which can prove interesting theorems. For example, Galva theory shows that you cannot express roots as formulas using square root, cube root, fourth root when the degree of the polynomial is 5 or more. Okay, so the impossibility results become possible by Galva theory. So here we will use something called Galva field named after him. So Galva field is a special finite field, and you can show as a homework exercise that when your finite field is finite, when your field is finite, then you have control over its size. So finite fields are of a very special size. They are somewhat like prime numbers. In particular, a Galva field always has size a prime power. P, in this case, p to the e, p is a prime. And in this Galva field, when you add 1 to itself p times, you get 0. Okay, so that is called characteristic. So the period of one is a prime number, and that determines the size of the Galois field, of the finite field. So this is something very special that happens in finite fields, that you have one-to-one correspondence with the prime numbers. So these are like algebraic versions of prime. Primes are number theoretic, Galois fields are algebraic. So I like these a lot. I use these in a lot of my problems, and computer science has tons of applications where these finite fields are used, because computers can only store finite objects. So now you are given a polynomial f of x over a finite field. Let us say it's a finite field of numbers 0, 1, dot dot p minus 1. So Galois field of size p. And the question is again, computational question is to factorize it. So for example, if you look at the univariate polynomial x square minus 2, over integers it will not factor, but modulo 7 it will factor. Why? Because 3, 3 square is 2. Okay, so since square of 3 is 2 mod 7, so you see that x minus 3 and x plus 3, or x minus 3 and x minus 4, these are factors. Okay, so this quadratic polynomial actually factors. So this could be a bit confusing when you move from integers to finite fields. So in integers, the polynomial is irreducible, but over the finite field, it is reducible. And you will lose track of your basic intuition. So can you do irreducibility testing here? So the L-cube algorithm, which we saw on the previous slide, that will not work here, because that uses real algebraic geometry. So it will not apply to this finite field setting. But there are some other amazing properties that start appearing in finite fields and polynomials over finite fields, which were used very early on, even before actually when integer polynomials were factored. Even before that, Berlekamp and Cantor-Zassenhaus gave multiple algorithms. And what they use is, unsurprisingly, they use the Galois automorphism. Okay, the group structure, that sits behind these finite fields. So it's a very simple algorithm ultimately to implement. All you have to do is you have to take GCD of your polynomial input polynomial fx with the very special polynomials, which I call Galois polynomials. So this x raised to p raised to e minus x. So x raised to p minus x raised to p square minus x raised to p cube minus x, and so on. So you take GCD. Now GCD algorithm, I think all of you know what GCD algorithm is, Euclid GCD algorithm. You have seen it in your basic C programming, and you have seen it in your basic math courses, how to take GCD of numbers, greatest common divisor or highest common factor, GCD or HCF. And same thing you can ask for two polynomials. What is the highest common factor or greatest common divisor? And there is this very classical 2000-year-old algorithm given by Euclid, who was another great ancient Greek philosopher and geometer. So that algorithm happens to be the first very fast algorithm that you can implement on computers, and using that you can compute the GCD, and using the GCD you factor F. Okay, so that is how factorization happens over finite fields. And this is useful in in several cryptographic systems, encryption, decryption. It is useful in coding theory. In fact, error correcting codes are very critical for computers. So if error correcting codes were not there, then computers also will not be there, because circuits are always making mistakes. Electric current, when it is flowing or when you store electricity, there are many physical faults. So how those physical faults are to be managed and data integrity is to be maintained, for that you need error correcting codes, which are actually codes or methods using finite fields. Uh, the other applications are in computer algebra, computational arithmetic geometry, and more advanced topics. So this has tons of applications, and this algorithm is very practical. Any questions at this point?
No, right now, sir.
Oh, your students understand everything.
Yes, sir.
Okay. So then we move to the next object, which is Galois rings. So what we just saw was Galois field, finite field. So integers modulo 2 is a finite field. I don't want to exactly define what a finite field is if you don't know. But it is just a method. You can think of it as a mathematical object where you can add and multiply, and you can subtract and divide. Okay, so any object where you can add, subtract, multiply, divide, that is called a field. So you can do that in integers modulo 2, and then you can also do that in larger extensions of Z modulo 2, which is the Galois field of size 2 raised to e. So this is called a degree E extension of the basic finite field, prime finite field. And what is a Galois ring? So Galois ring is where you may not be able to divide. You can only multiply and add, and it is somehow connected to this structure. So it is on the right side. So integers modulo 4, you cannot divide by 2 because 1 upon 2 does not exist modulo 4. This is called the problem of division by 0. You cannot divide by 0, so you can't divide by 2 here. But this Z mod 4 still has some nice properties. For example, you can do mod 2 and you can come back to the field. So what is the analogous object for the bigger Galois field, GF 2 raised to E? So that is called the Galois ring. It's a degree E extension, and it has 4 raised to E elements. So you can think of E equal to one case for this talk. In this talk, you can think of Z mod 2, Z mod 4, Z mod 8, and so on. But the point is that for Galois fields also there are these analogous objects. These are beautiful objects. They are called Galois rings, and they are very tightly related to Galois field properties. You can lift all those properties. So in general, Galois ring GR, we'll call it now, is of size p raised to k multiplied by e, and the characteristic is p raised to k. So in Z mod 4, for example, characteristic is 4 because you add 1 2 times, 3 times, you will not get 0. But when you add it 4 times, you will get 0. So that's the period. So the period of 1 is characteristic, and that happens to be p raised to k in a Galois ring. And then when you go to an extension, it becomes size becomes p raised to k e. So now you can guess the problem. The problem is given a polynomial over such a Galois ring. Can you factor it? Can you find a root? So the previous example, since it is tightly related to Galois ring, Galois field, Galois ring both, actually continues to work. So x square minus 2 will factor mod 7 square also. So mod 49 also it has factors because x minus 10 is a factor. Okay, 10 square is 2, 100 is 2, mod 49, right? 100 minus 2 is 98, which is a multiple of 49. So x minus 10 divides, and so x plus 10 also divides. So x square minus 2 completely factors, but the question you should ask is whether this is a unique factorization. So in this case, you can show that actually it uniquely factors. These are the only two factors. There are no other factors. Uh, now, is that true in general? So we'll see that that is not true in general, and which is why we get kind of stuck. I think I don't have an example here. Let me see. Yeah, so here is an example at the bottom. If you look at x square minus px mod p square, so if you look at, for example, x square minus um, 7x mod 7 square, then the problem is you will have many more roots than just two roots. So the factorization, the roots are not unique. They are not limited. They may be tremendous in number. So that is the problem. That here in x square minus 2 mod 7 square, the roots are only 2 and there is a unique factorization. But in general, that is not true. So factorization may be in many ways. And so it becomes actually hard to create a theory of factorization. And so irreducibility testing here has been an open problem for a long time. This problem is still open. How to test that a polynomial over a Galois ring is irreducible. So this is an open problem. The only known solution for this is brute force, which is very expensive because your prime p can be very large. Your k is in the exponent, so it will take p raised to k time. So there is no practical algorithm for this. But in my group, we have solved some special cases. For example, when k is equal to 4, 1, 2, 3, or 4, then we can solve it efficiently. There are fast algorithms we designed. So factoring fx mod p, p square, p cube, p4. These algorithms we have designed, which are fast. So the non-triviality here is how to lift a factor from mod p to mod p square. That is the primary challenge. Because there is no formula which tells you how the lift will happen, because the lift is not unique. So lift may have exponentially many ways, and exponential means p many ways. So you have to try all of them, and that becomes very, very slow. It's a bad algorithm. So we find clever ways. And so yeah, so these two examples are very different. This x square minus p versus x square minus px are very different. The first one is irreducible, while the second one is reducible. It has roots. It has in fact p roots. So it has degree only 2, but if p can be arbitrarily large, p may have thousands of digits, and then there are 2 raised to 1000 roots. So a tremendous amount of roots. You cannot actually store them in a data structure. It's too expensive. So that is the challenge that comes in factorization over Galois rings. So this is the first integer factoring I told you is open, and now this is the second open problem: univariate factoring over Galois rings. In Galois ring, you can take k to be very large, and then it becomes what is called p-adic numbers. So this was studied and defined and invented by Hensel in 1800s. So Hensel defined p-adic numbers. So these are actually limiting Galois rings. So you don't stop at p raised to k, you continue till infinity, p raised to infinity. So you say that 1 plus 2p plus 3p square plus 4p cube plus 5p4 plus dot dot till infinity. You can keep filling in values, and that is also a number. So that these numbers are called p-adic numbers. And Ramanujan and The number theorists routinely work with p-adic numbers. So this is very close to um, many number theoretic uh, problems and studies and methods. And so this is also of some interest in computer science, in algorithms. And so we can ask this question, given a polynomial over p-adics, can we factor it? And interestingly, this example continues to be a positive example, x square minus 2. So in x square minus 2 also has 7-adic factorization. So here it is. So what I showed you first was 3 square root 2 3 mod 7. Then I showed you square root 2 is 10 mod 7 square. And now you can check that square root 2 is um, I think 108. Square root 2 is 108 mod 7 cube, and square root 2 is this 108 plus 6 times 7 cube mod 7 to the 4. So you can keep on doing this. So you can go to any 7 raised to k, and the initial part will give you square root 2, which will be a root of f. So we say that since we can keep on doing it till infinity, this is the answer. This is the root, 7-adic root of f. Okay, so this is possible because 3 is lifting in a unique way. Okay, 3 lifts to 10, then 10 lifts to 108, and then that lifts uniquely to something else, and so on. So you can keep on doing this till infinity, and number theorists call this a p-adic solution. This is a p-adic solution, and this is what Hensel invented. So the question we are asking is, given a polynomial over p-adics, can you check whether it is irreducible? And if not, can you find a factor? So this picture below shows that here in p-adic numbers, our word view is inverted. Okay, so for integers, the word view is as the integers become bigger, they go away from 0, far away from 0. In, let's say, two-adic, the two-adic word view is that as the 2 power increases, you are getting closer to 0, which is very strange, right? So 2 raised to 0, which is 1, is considered very far from 0, but 2 is considered closer, then 4 is considered even closer, and then progressively 8, 16, 32 are getting closer and closer and closer to 0, and when you reach 2 raised to infinity, that's considered equal to 0. Okay, so this is the inverted um, topological viewpoint, and so it gives some very interesting results, different from complex analysis or real analysis, and generally it is applicable to our computer science discrete questions, so it's more amenable. So there is actually an algorithm, not very old, around 3 decades old. There is an algorithm which can factorize over p-adic numbers. Okay, so in this these kind of numbers, when you look at univariate polynomials, there is a fast algorithm to factorize and check irreducibility. And the idea is very different. It starts because there is no Galois group, there is no group, there is no lattice, so we can't actually use the methods that we have seen in the previous slides. Here the method is very different. It's something to do with the Newton polytope. If you have seen in engineering, Newton polytope method is used here. And ultimately this reduces the questions to uh, modulo P, the Galois field factoring, which we know how to do. So it's basically a complicated induction from Galois field factoring to p-adic factoring. And this problem is useful in computational number theory in other areas of mathematics. Um, it is good to know this algorithm. So in summary, we have fast algorithms to factorize univariate polynomials over p-adic numbers, over usual numbers, that is integers, and over Galois fields. Okay, so three important math areas. We can factorize polynomials, break them into smaller objects, and write down very fast algorithms. So, which also means that we actually understand these objects pretty well. Compared to the one which is to do with Galois ring. Galois ring, we don't, there we don't understand factorization very well. So now I will move to multivariates. So that will be the generalization of this base case of univariate. So before I move to that, any questions?
Yes, sir. There are some questions, and we have scheduled our question answer session at the end. So can we?
Okay, we can, yeah, that also we can take, but right
Yes.
now, if there is a question, I will welcome it.
Okay. So there is a question that is there any application to Galois theory in the cryptography? How it is useful in encoding or decoding? It is from a
Oh,
participant.
yeah, so encoding decoding algorithms, both in cryptography and in coding theory, they work over Galois fields. So
Okay.
Galois field is the starting point and the end point. So every computation that happens in a Galois field. So it's not even important. It's not just important. It's actually critical. So if you don't have Galois field arithmetic, then you will not be able to implement anything.
Okay.
Any other question? I think there was some.
There are some questions. How can we relate the abstract concepts of algebra to
Mhm.
our daily life?
To our daily life.
Yeah.
Uh, well, in your daily life, if you are using bank transactions or if you are using secure HTTP, then you are using it without knowing. So, which is fine if you just want uh, that application as a tool. But suppose you want to actually understand how that tool works, and if you want to create a company which runs on a faster tool, then you have to understand these abstract concepts to be able to improve them. So it's only if you want to improve something. If you don't want to improve, if you are happy with your life, then abstract concepts are not needed.
Yeah.
But if you are unhappy with your life, then you have to go into abstraction.
Yes. And so there is one more question, sir. Is it always
Yes.
possible to factor an expression or number, or there is some bounds?
Yes, so number is this integer factorization problem, the first problem I mentioned. Right, currently it is not possible to factorize big numbers. So I mentioned that it's an open problem, by which what I mean is that if you give somebody a 500 digit number, then it will be very hard to factorize it. So there are very fast algorithms to check for primality. So one can check for very big numbers, whether it's prime or composite. That can be done very fast in seconds. But even after knowing that it's composite, finding an actual factor, it's very hard, and there is no known algorithm to which works generally beyond 500 digits. So up to 500 digits, there are these hacks, number field sieve, elliptic curve based factoring, and other methods, but uh, they become extremely slow at the range of 500 digits, 1000 digits. After that, they become impossible. You won't get an answer. For expression, so by expression, I mean I think you mean polynomials. So for polynomials, I've been giving you slide after slide examples. So those expressions or polynomials can be factored fast, except the one which is over Galois ring. That is again, it's an open.
Okay.
Currently, it's an open question.
I hope they got their answer.
Okay. Yeah, if
Thank
not, then they can ask more.
Sure, sure, sir. Thank you, sir.
So how much time do I have now? 5 minutes.
Yes, sir, you can continue.
Okay. So multivariate is, I will just mention the model. What does multivariate mean? Because some of you might never have seen it. So, so multivariate means that you are interested in some function value, but that value depends on many parameters, right? So here there are some silly examples like level of education. It depends on you can deduce level of education by looking at satisfaction of a person in life or satisfaction of a person in a job. Or you can try to deduce level of education just from satisfaction in life, right? So one parameter, two parameter, or 100 parameters, it depends on how much information, how much data you have. So multivariate means that there are many parameters, and from those parameters, you want one answer. So till now, what we have been looking at is univariate. There was only one parameter x, but as you can imagine, in real life, it's always multi-parameter, multivariate functions. So how do you store those functions? How do you calculate those functions? How do you work with those functions in a practical, fast way? So that is done by one is this dense representation. So in the dense representation, you are given a polynomial f and you want to factor it. So in this representation, you just write it monomial by monomial. So that's called sparse. You call it a sparse polynomial. So here, for example, if you write this x1 to the d minus 1 dot dot xn to the d minus 1 in monomials, then you will get 2 raised to n many monomials. Okay, so these are the monomials. You store them in an array or in a data structure. And then you can see that there is a different polynomial g, which is this first factor is x1 to the d minus 1, then second plus x1 to the d minus 2 dot dot x1 plus 1. And then the same thing with x2, same thing with x3 dot dot, same thing with xn. So this, on the other hand, has d raised to n many monomials, right? So you can see that 2 raised to n many monomials can be divisible by d raised to n many monomials. So the problem that happens with multivariate, this curse of dimension, the curse of dimension is that the sparsity blows up very fast. So 2 raised to n becomes d raised to n. So this is called super polynomial blow up. It's a huge blow up, so which means that factors can be very large. So if factors are very large, you cannot store it in your hard disk. It's much bigger than the input. So that is the problem that we face. And so there are many questions about what can be done. So let me skip those questions because this gets more and more technical. So there are some results known, and this again uses Newton polytope. We have results by Newton polytope, but mostly these questions are open questions. And in general, the question is impossible to solve because, as you saw this example, the factors do become very large. So there is only so much you can do in this area. So Instead, we look at a more computer sciencey representation, which is that of a formula. Okay, so what is a formula? A formula is what you write in your notebook. It's basically you start with x1, x2, x dot dot x6 in the input, then you add those variables, then you multiply those answers, then you add those answers. You can multiply them with a number like 9, you can multiply them with numbers like -2, and so on. And after several such operations, you get a polynomial which is f of x in 6 variables. So this is the formula representation. Here you don't see the monomials. All you see is that you are adding or multiplying. Okay, you don't see the monomials. Monomials are hidden. So this is a more compact representation. You can also think of this as a C program. So it's basically a C program that is given to you in uh, a simplistic way to say is that you are given kind of a program, and the program is ultimately a polynomial. You want to factor it. And then how will you output the factor? Well, the output of the factor has also it should be given as a program, right? Input was a program, input was a formula, output also should be a formula. So if it is a formula, then what is the size? How big is it? Can you store it on your hard disk? So this is what you want to study. You want to study factors and their sizes for a given formula of sizes. And this there was no good result known till last year. So till 2024, there was no good result known. There was only some super polynomial results known, which means that just like sparse representation on the previous slide, here also the formula factor would blow up, and then you will not be able to store it in your hard disk. But this year, there was a breakthrough by 6 authors. So these Indian authors, they showed that factors of a formula are also small formulas. Okay, so this was a very recent result, just 6 months back. So what they do here is they use a classical complex analytic result, which is called Lagrange inversion formula. So Lagrange inversion formula is a way to invert a function. So if you are given a function f and you want to invert it, you want to calculate f inverse. So f inverse is g. Then what is g? So it gives a nice compact expression for f inverse. Okay, so from one analytic function to its inverse, this is what Lagrange inversion formula connects. This is a very classical result from 1800. So using this, these 6 authors, they give a formula for the roots of the input formula. So for the input formula, how do the roots look like? They use Lagrange inversion, and it happens to be a simple formula just like Lagrange had given. And from there, they are able to build the output formula. So this problem also gets solved. And with this problem, many other problems get solved. Many questions about circuits, constant depth circuits. So circuits are similar to formulas, but here you are allowed to use an output multiple times. So for example, this x1 times x2 in the bottom, this output is being used twice. So, and then x4 is being used twice. So you are allowed to use a polynomial as many times as you want. So that is called a circuit. And constant depth means that the number of layers is constant. So all these models have similar sized output factors. So this also gets shown. Uh, so constant depth circuits, formulas, um, circuits, something called algebraic branching programs, all these models get solved simultaneously by Lagrange inversion based expression. What is still open in the circuit model is the question of very high degree. So in a circuit, what can happen is you can produce very high degree monomials by repeated squaring. You feed x 2 times and then you will get x squared. Then you feed x squared 2 times, you'll get x to the 4. So in s multiplications, you can get to x to the 2 to the s. So that's exponential degree. So in these cases, we don't know what to say about factors. Okay, so this question is still open. So let me not get into the details of that. Let me conclude now. So the open problems, just to enumerate again, how to do fast integer factoring. Second is how to factor fast over Galois ring, that is mod p raised to k. General circuit factoring, that is when the degree is very large, what kind of a factor do you get? And fourth is de-randomization, which is more of a abstract question that can all these algorithms actually use coin tosses. They use random bits. They are probabilistic. So is probability necessary? Can you eliminate probability from these algorithms? That's the de-randomization question. Thank you. You can read the survey on my homepage. There is a factorization survey with more details. So thanks. You can ask questions.
Thank you, sir, for the insightful and inspiring oration. Now we are open for the question answer session. Sorry, there is a question.
Yes.
Can we use periodic number in improving iteration procedure?
Yes, so I don't know what Priya means by iteration procedure. Uh, can you ask her what can we discuss this with her, or
Priya
is
ma'am,
she allowed to
So yes,
unmute?
sir. Actually, she is asking about the iteration procedure, like Newton-Raphson iteration procedure, something.
Okay. So it is a good question. If she means Newton iteration, that is a good question. So Newton iteration is a different kind of adic, I-adic procedure. So p-adic numbers give you a series in powers of p, while Newton-Raphson iteration method gives you a power series in maybe a variable x. So when that happens, you call it an x-adic calculation. So Newton-Raphson is also trying to do that. I mean, trying to do this analogous to number theory. But I mean, whether it improves something in practice, for that you have to do a comparison. Like, what is the input? Are there any special properties? So using those properties, you can improve the time complexity. But if it is very general, then you will just get whatever the theorem of Newton iteration tells you.
Thank you, sir. Is there any more questions from participants or panelists? So I hope all the questions are answered well. Thank you so much, sir. Now, I request Dr. Seema Bagora, co-coordinator today's program, to present the words of thanks. Please, ma'am.
Thank you, ma'am. Good afternoon to all. I deem it a great honor propose the vote of thanks on this occasion. Let me first of all start by giving glory to the Almighty God for making today's occasion successful. First and foremost, I thank you today's speaker, Dr. Nitin Saxena, Chair Professor, Computer Science and Engineering, IIT Kanpur, who despite his busy schedule has found time to grace this occasion. I thank our sources of inspiration, Honorable Vice Chancellor Dr. Yogesh Chandra Goswami, Coordinator SVIS Dr. Uttam Sharma, Head Department Mathematics Dr. Satish Shukla for their support and guidance. My heartfelt thanks to all the faculty, staff and students of Shri Vaishnav Vidyapit Vishwavidyalaya to their support. Last but not least, I thank you to all who have worked hard to ensure that this occasion becomes a memorable success. Once again, I thank you all for your attention. Thank you. Thank you very much, sir.
Thank you, ma'am. Now, for the photograph of today's program, I request everyone to please turn on their video. All the panelists, please turn on their video. Is it done? Is it done, sir? Thank you. Thanks to our technical team. Now, we shall now conclude the event with our national anthem. Please rise, all of you, for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
भारत माता की. Once again, thank you all for your gracious presence. Thank you, sir. Thank you, Saxena sir, for your oration. And thank you
Thank you
all.
very much, sir.
Thank you, sir.
Thank you, Dr. Nitin ji. धन्यवाद.
Thank you, sir.
Thank you.
Thank you, sir. Thank you.
चलिए, then I leave. Okay, thanks. Bye.
Thank you, sir. Okay, sir. Thank you, sir. Thanks to all.